Hello everyone, and welcome to TechnoBoss. I am MacGyver, and today we, to include me, are going to be learning some basic programming and circuitry based on the Arduino platform. The kit that I'm using is the Artist DIY kit that I found on Amazon for $83. Take note, none of this is sponsored by anybody. Okay, I wanted to learn some of this stuff, and this kit looked like it might actually fit the bill. Lesson 3, controlling an LED with a button. Now, before we get into this lesson, got a quick little announcement to make. As you have probably noticed, this looks a little bit different than the original manual. I have gone through and I've done a little bit of editing in order to make it a lot easier to read. This should hopefully do better. With that out of the way, on to the lesson. Overview. In this lesson, we will learn how to detect the state of a button and then toggle the state of the LED based on the state of the button. Okay, requirements are Arduino board, a USB cable, a button, an LED, a 10K resistor, a 220 ohm resistor, the breadboard, and at least 7 jumper wires. The principles. The button. Buttons are a common component used to control electronic devices and come in a variety of sizes and shapes. They're usually used as switches to connect or disconnect circuits. The one used in this experiment will be the 12mm button as shown in the following picture. This is a normally open type button. The contacts of the button are in the off state under normal conditions. Only when the button is pressed they are closed. The schematic diagram we use is as follows. Pins 1 and 2 are connected, pins 3 and 4 are connected, but 1 and 3 are not connected until we press the button, and then everything's connected to each other. The button jitter happens when the button is pressed and released. The jitter waveform is represented by the following picture. Each time you press the button, the Arduino will think you have pressed the button many times due to the jitter. We must deal with the jitter of the buttons before we use them. We can remove the jitter with a programming or software method, or you can use a capacitor method. We will introduce the software method here. First, we detect the state of the button interface, low level, closed or pressed, or high level, open or released. When a low level is detected, a 5 to 10 millisecond delay is needed to allow the jitter to pass. Then a check is made to see if the level of button interface is low or high. If the signal is low, we can confirm that the button is pressed. So it thinks the button's pressed, waits, checks. Is it not? Okay. So this is basically how the circuit looks. So we have a constant 5 volts going through a 1K resistor, a general purpose in and out, and then the button just goes straight to ground. So it looks like you're just grounding out the circuit in order for it to look like the button is pressed. You can also use a 0.1 microfarad capacitor to clean up the jitter of buttons. The schematic diagram is shown below. And here they just have a 0.1 microfarad capacitor that looks like it's parallel to the button. So when you press the button, with how capacitors work, it'll basically keep a power for that little frog hair at a time for the jitter to pass, and then when it runs out of power, it's like, oh, wait, button's pressed. Interrupts allow sections of code to be skipped until an outside event happens. This frees up processing time for other tasks. Okay, so we're going to be dealing with an interrupt, okay? The key function, attach interrupt, okay. Digital pin to interrupt pin, ISR name, and mode. This specifies a named section of code known as an interrupt service routine, an ISR, for changing the value of a global variable when an interrupt occurs. In our case, pressing a button. Most Arduino boards have 2 external interrupts, digital pin 2 and digital pin 3. Generally, an ISR should be as short and as fast as possible. If your sketch uses multiple ISRs, only one can run at a time. The interrupts will be ignored until the current one is finished. The functions delay and millis both rely on interrupts. They will not work within an ISR. Micros will work initially, but will rapidly become erratic. So I guess not use micros either, okay? Delay milliseconds, which does not rely on interrupts, will work as expected within an ISR. I guess this means we're using delay microseconds when we make a interrupt service routine. The syntax. Attach interrupt is the name of the command, parentheses, big parentheses here, digital pin to interrupt, small parentheses, the name of the pin. Based on what was said earlier, I'm guessing we're probably going to be using pin 2, ISR, and mode. So let's check the parameters to see if my one guess was correct. Pin, the pin number. ISR, let's see, the ISR is called when the interrupt occurs. This function must take no parameters and return nothing. This function is referred to as an interrupt service routine. Yeah, the ISR is basically a small block of code, and whatever we call or title that small block of code is going to go up here where it says ISR. Mode. Mode defines when the interrupt should be triggered. Four constants are predefined as valid values. Low. To trigger the interrupt whenever the pin is low. So whenever the pin is grounded out, it is triggered. So as long as it reads grounded out, it means it's triggering the interrupt. Change. To trigger the interrupt whenever the pin changes value. So basically, if it goes from high to low, low to high, if any one of those happen, it's getting triggered. You press the button, it's triggered. You release the button, it's triggered. Rising. To trigger when the pin goes from low to high. So in our case, that would be like when we release the button, because it's on low when you're pressed and high when you release. So that means you'll only trigger it when you release the button. Falling. For when the pin goes from high to low. In our little example, whenever we press the button because it's going from a high state to a low state, that's when it will trigger. Which means when release, nothing happens. Digital read. Reads the value of a specified digital pin, either high or low. So this must be the command that we're going to be using whenever for the pin that is going to be reading the button. The syntax of it. Digital read, pin. Parameters, pin. The number of the digital pin you want to read. And then it will return a high or a low. Delay, microseconds. Pauses the program for the amount of time in microseconds specified as parameter. There are 1,000 microseconds in a millisecond and 1,000,000 microseconds in a second. That's a lot of seconds. Currently, the largest value that will produce an accurate delay is 16,383. That's a big number. This could change in the future Arduino releases. For delays longer than a few thousandths microseconds, you should use delay instead. This comes back to what I said earlier, how it should be as short and as fast as possible. Syntax for the delay microseconds. The US is the number of microseconds to pause. They want us to use milliseconds. Okay, they said 5 to 10 milliseconds earlier. That's going to give us a value of 10,000 microseconds. Okay, next, a volatile integer or volatile int, a global variable that is saved to RAM instead of storage so that it can be changed later in the code. When we put down all of our global variables, we'll have one that is going to need to be changed. That's going to have the volatile in front of it. Syntax, volatile int name equals variable. Name, the name used in place of the variable throughout the program, the variable or the assigned data. So I think that's going to be like a 1 or a 0. I am guessing 0 for off, 1 for on. And what we're going to be doing is changing that. Then of course procedures, we're going to build a circuit, program, ooh, hey, yay, we got program. We're going to go ahead and put together the board, then we're going to program, and then we're going to see what happens. Doesn't look too bad, but I'm pretty sure we can screw it up. Alrighty, so we have our Arduino board. We have got the USB cable off screen. We've got our button. Nice red 12mm like in the picture earlier. We have got our 10K resistor. We've got our 220K resistor, our LED, breadboard, and 7 jumper wires. So let's go ahead and let's start getting this thing all put together and figured out. So we're just going to move these off to the side right now, and we're going to start populating this breadboard. So let's see here. So this must be the even pins and the odd pins, or vice versa. But it looks like this side goes on one area, this side goes on the other. So we're just going to put it somewhere right on down in here. Come on, come on, there's that. And there's that. So nice and in there. Okay, boom, 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 we got a pin, or we got a button. Okay, and we have our LED, and we have the anode and the cathode, and the electricity is supposed to flow from here to here. So we're going to have it going that way. So we're just going to pop it right here on the board. There we go. We're in. Okay. Then the 220 ohm resistor is going to go right before it. Whew. Yeah. I'm going to use these to help make sure that I get it in without damaging it. Okay, there's one. There's two. That's all the way in. That's all the way in. Okay, one resistor's in. Now the next resistor, we're going to bend these into nice little legs. And this is going to be on the button. Okay, there's one in. And that's two in. Okay, so basically power's going to flow over. So power's going to come into the board here and is going to go this way and then back to ground. So let's go and start with our hot, which is going to be our 5 volts. So that's going to be, let's see here, that's in, ground, ground, 5 volts. And we're going to just put this anywhere on this red line. So we'll just put it right here because this whole red line is connected. And then we have ground. And we're actually going to use this ground over here. We can actually use any of the grounds on the board. I'm just using this one. And we're just going to bring it over here and put it in next. So, red is hot, blue is ground. Next, let's go ahead and get this LED wired up. And this is going to be on pin 13 from the looks of it. No, correction. The little diagram here shows pin 11. So we have 8, 9, 10, 11. And this is going to go towards the hot. Oh. That's bad. Let's straighten that out. Okay, let's try that again. Hot. There it goes. So that is now in line with this leg of this resistor. And that's just going to go in. Then we're going to do a blue wire going from the anode of the LED, and we're going to send it straight to ground. Then we're going to do an orange wire, plug it in right next to this resistor, which is going to the button, and this is just going to plug right into the hot. We're going to take our nice little purple one after the resistor but before the button, and this is going to get plugged into pin 2. So here's 0, 1, 2, because we're going to be using pin 2. And then our last one is this green, which is going after the button and is going to ground. Alrighty. So after the button is going to ground, before the button is going to pin 2, before this resistor is going to a constant hot, this other resistor before it is going to pin 11, and after the LED is going straight to ground, and then we got both ground and hot. So that's all wired up. We should be able to start programming. Alrighty then. Okay, let's start doing some coding. So let's get some space up here at the top, and we got to do our global variables. So our first one is going to be, looks like pin 11. So let's see here. int for integer, LED pin equals 1, 1. Okay. Then our next integer, button pin. They just did BT. I'm going to just spell that one out. Button pin. Pin equals 2. Then a volatile. Okay, so let's see here. F. Where'd F come from? VOLATILE INT state equals low. Wait. Capital. Void setup. Get rid of all this. So the setup, pin mode. LED pin and output, all caps. Wait, hold up, semicolon, 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 semicolon. Otherwise, I might have some problems. Then, let's see here. Next one is attach. Whoa, not caps. Attach. Whoop. Interrupt. Okay, digital pin to interrupt. Okay. The pin is going to be button, pin, comma. Okay, so now we got to name what we want our ISR to be. They're saying state change. I'm saying change state. Woo! Change state. And they're wanting us to do low. Well, we can go back and we can play with that later. So let's start with low. And then semicolon. Okay. And that should be it for the void, for the setup part. Next, the loop. Alrighty. And delete all that. Digital write. LED pin state semicolon. Oh, not colon, semicolon. Okay. Then it looks like the loop's actually done. Void change state. This is making it to where this is going to be our interrupt. So when we press the button, it pops out of the loop, goes to this, then it just goes back into the loop. Curly bracket. If, aha. So we got parentheses, digital read, parentheses, and this is where we're going to have button pin. Oh, I'm going to have to fix that because it has too many T's up here. Let's fix that. Okay. So parentheses, button pin, and then equals equals. So I believe that's, yeah, so that's just basically if button pin is low, okay, delay microsec, seconds, parentheses, 10,000, semicolon. So it's a read, delay, reread. And then, so if, and we're just write the same thing, digital read button pin equals equals low curly brackets, okay, state equals apostrophe state, semicolon. Oh, because I think the apostrophe state is going to change it over. I guess let's see if this code makes sense. Compiling sketch. No strange. I guess it makes sense. Alrighty, let's plug in the Arduino board. And again, let's hope that we don't get any of the magical blue smoke being released. So, plugging in. Okay. So far, so good. So upload. Oh, wait, hold up. No upload port provided. Uh-oh. Oh, here we go. Now upload. Okay. It's done. So, no magical blue smoke. No work either. What'd I screw up? Uh-oh. Oh, wait. I wonder if it is literally as simple as turning this around. It is not. I screwed up somewhere. So here, pin 11, pin 2, Okay. Huh. What is going on? Let's see what we get. Because I know with breadboards, all that is supposed to be connected. Okay. I think this breadboard is so cheap that each one of these sections, because ooh, wow. You got to press it for a while. Hmm. Well, well, that's working. Or is it? Yeah, no, that is working because change state to low. And, huh. So let's go ahead and change this to falling. Check. Upload. Compiling done. Oh, that seems more stable. Okay. Which means we should be able to change this to rising. Oh my goodness. Let's try that again. Check. Okay. Go. So if I press, nothing happens. But if I release, oh. It doesn't like that. Hmm. Falling worked pretty good. Let's double check. Woohoo! Falling. Upload. Oh! If we change this to, I think this has to be changed to high. Then we come back here to rising. Verify code. Okay, let's load it. Then that should make it Still not working. Okay, what about? Woohoo! Too many letters. Hi. Aha! Okay. Okay. So if we set this to change. Okay. So for rising, they both have to be high. For falling, they both have to be low. For low, they both have to be low. That seemed a little unstable. Okay. Um, I wonder if maybe change? I don't think that's going to work. But, let's see here. Compile's okay. We got that. Okay. Um, hmm. Well, that's not quite working how I expected. Huh. Yeah, but I don't know. Play around, see what you come up with, because you might discover something that I'm missing. I encourage everyone to play with the code more and challenge yourself to see what you can make. If you like what you see, find this video helpful, please like and subscribe and click on the bell icon to be notified when new videos come out. Thank you for watching. Good luck, have fun, and stay curious.